Hello, everyone, and welcome back to our discussion about the unit circle. Before I proceed, I would like to thank you that you are being patient and understanding because I couldn't upload multiple videos last week. Last week, I had other duties or priorities rather that I must accomplish. So I would like to thank you for that. Okay? And maybe I will also, let's just say, uh, maybe I might have that scenario again in this week. Okay, but no worries. I'm still continue to upload these videos, especially the calculus one. All right. So without further ado, let's now begin. So last time we knew about the unit circle with the application of having inscribed square or square inside a circle. Then in the first part, we also discussed like the what do you call this one? A circle that is divided by four congruent parts, okay, or four congruent arcs rather, or it's divided by its axis. Now, what if we have an inscribed hexagon or an hexagon inside this circle? Oh, wait. There you go. So here we have a regular hexagon. So here, to give you a, let's just say, background information about this so-called hexagon. Hexagon is a six-sided regular polygon. Okay. So what do I mean by regular polygon? That means that not only that the side lengths of each of the sides here, like this, and the other sides are equal to each other, but the interior angles or angles within the shape found in each of the vertices are all the same. So again, not only that the side lengths are all the same, but also the interior angle. So the angles here is the same, the same, the same. Okay. So our goal here is just like what we did in the last video. I mean, recent video. We're going to find the coordinates, okay, of each of the vertices. We're not going to find the arc length because we already knew that what would be the magnitude of the angle. That would be also the how should I say this? That will be also the magnitude of the arc length. Okay, so we will find six of these vertices. However, I think we're just going to find only four of these. Can you guess why? Why do you think that I'm just going to discuss only discuss? I'm just only going to find four vertices only. It's because that we already knew the coordinates of these two. Okay. Remember in our first part that if let's just say the terminal side is along the axis or along the quadrantal angle, like this basically, these two, you will have the coordinates, which is either 1, 0, negative 1, 0, 0, 1, or 0, negative 1. So here, on the right side, this is actually 1, 0, and on the left side, this is negative 1, 0. Okay? I discussed this one on, to be particular, the first part of unit circle. So if you have no knowledge about it, I suggest you should watch that first. Okay? So due to this, we're not going to discuss this anymore. Okay? So once again, if you want to know more information about this, I suggest you should watch the first part of this topic. All right? So let's find the vertices of these four. Okay? So how can we find the angle here? Because you see, I think we discussed like how can we find the angle here form until we reach that vertex. Like that's like for a square, right? We knew, like for example, that we have a square divided by 4, and we want to find the what's that again? The vertex here to be particular, and we what I call this one. We get the angle here, which is 45 degrees, right? We knew that because of the angle or the properties of a square, and of course the how should I say this? The special right triangle, which is 45, 45, 90 degrees, right? So how about this one though? So let me draw a regular hexagon. Please imagine that this is a perfect regular hexagon. I'm not good drawing this, especially that I use my mouse to write. Okay. So this is a regular hexagon. Okay. So here we can actually have multiple equilateral triangles in here. Like, think of it like a pizza. So we can have all of those pizzas form together and it will form like a circular shape, right? So this one, similarly speaking, we can have equilateral triangles to form a regular hexagon. What is an equilateral triangle? An equilateral triangle, basically, it is a triangle that has sides that are equal to each other. So for example, if this is 4 units, then that means the other sides should be also 4 units. Okay? Not only that the equilateral triangles have equal sides, but they also have equal interior angles. What does interior angles means? Meaning the angle formed by the vertex. An interior angle is within the shape. So it's just like this one. Okay? So these interior angles are all the same. Okay? In fact, these angles are 60 degrees, 60 degrees, and 60 degrees. So they are all the same. I think there is a what's that? I'm not sure, but let me just share for a moment. I think there is a Facebook post that I've seen before, and I saw a post that shows that not only equilateral triangles that has 60 degrees only, but they also have equilateral triangles that are not 60 degrees, but they are actually all the same. Like if I remember, 69.5 degrees, then 69.5, then 69.5 here. So I could be wrong, but usually it is 60 degrees. Okay, so that means an equilateral triangle not only have an equal length of each sides, but they also have an equal length of the angles, interior angles to be particular, which is this one, 60 degrees, 60 degrees, and 60 degrees. In fact, once again, the interior angles of the equilateral triangle is 60 degrees. So how can we form that? So this is actually how it looks like. Okay, let this be the center. Okay, so there you go. Okay, so here, uh, 1, 2, 3, 4, 5, 6. There are a total of 6 equilateral triangles. Okay, there are a total of 6 equilateral triangles. And remember that in an equilateral triangle, what I told you earlier, that not only that they have the same sides, but they have the same what? Angles. Okay. So that means, oh wait, whoa, whoa, whoa. So that means, okay, here we have 60 degrees, 60 degrees, 60 degrees. Okay. Let me just erase the number so that we can have space. 5, 4, 3, and 2. Okay. So we have 60 degrees here. What's next? Yeah, 60 degrees here as well. Okay, then 60 degrees, 60 degrees. Okay. So I think you get my point. All right. So yeah, these are all 60 degrees, especially on each of the vertices. Okay, 60 degrees, 60 degrees, 60 degrees. Let me just write it all over so that I think, so that you can get the idea. All right. So yeah. So you see, this is also applied in this case. And here, let's start finding the how should I say this? The vertex of this. I mean the coordinates of this vertex. Let's find the coordinates of this vertex. So here It's just the same as this part, which is we start from the center, then we draw the line here. Okay? And remember that this is 60 degrees, 60 degrees, and 60 degrees. Okay? Just like this part. Okay? Just like this part. This part. Okay? This one. All right? So I'll erase this one because I already explained it to you that each of the sides there are 60 degrees. I mean the vertices I mean. Okay? So I'm gonna erase this one. Okay, so yeah, 60 degrees. Okay. So here, how can I find the, like the vertex, or sorry, the coordinates of this vertex? Okay, how though? So here, we're going to find this one, right? So similarly, like what we did on the last time, which is in the square, right? So we have a square here, and we're asked to find the vertex here. So this is the origin, and this is the the terminal side. So all we need to do is find the x coordinate and y coordinate, which is actually what, a right triangle, right? This is actually a right triangle. In a square, this is 45-degree, and this is 45-degree. Okay. So here we will do the same thing. Okay. So here we will find the horizontal, then it's vertical. So here we will have vertical here, vertical line here, and we have the horizontal line. Okay. So this is 60 degree again. And you know that this is, what do you call this one? This is 60 degree, right? This is 60 degree here. Okay. But you see, it's been cut by half here. If you would notice, so what happens? What happens is that, let me erase this one. Wait, let me erase. What happens is that in here, we will have 60 degrees and 30 degrees. And of course, a right angle. So this one again is being cut into half. So 60 divided by 30, so we will have 30 degrees. And here, we will apply one of these special right triangles, which is 30 degree, 60 degree, and 90 degree right triangle. Okay? We will apply 30, 60, 90 right triangle. So here, what's make it special because we can find exactly the what? The sides or the length of the sides, okay, of a right triangle. Okay? So let's find the coordinates. Okay? So here, let me just erase this one. All right? In here, if you have 30, 60, 90 degree triangle, what we will have here is that first, if you have the hypotenuse, okay, and you would like to find the measurement of the base, all you need is just divide the hypotenuse by 2. And if you wish to find the second longest side, which is this one, all you need to do is divide your hypotenuse by 2 and multiply it by square root of 3, or in short, h sine square root of 3 all over 2. Okay? So that is how you find the length of the legs, okay? If you have a given hypotenuse. Okay? So I hope you understand, okay? So by the way, if you're asking me why is it that it's we have a 90-degree angle, well, it makes sense because you see we form a straight line here, vertically speaking, and we have a horizontal line, which implies that the horizontal line and vertical line are both perpendicular to each other. So we have 90-degree angle, and according to the 90-degree angle, if, for example, if let's just say you have 30 and 60, so what would be the missing value here? So the missing value here would be 90 degree. And if, for example, you have 30 and 90, so what would be the missing value? So we will have 60 degree. And lastly, if you have 60 and 90, but you don't know the missing value, that would be 30 degree. So they go along, okay? So here you need to memorize this one. Actually, this is one of the basic geometry lesson. So I suggest you should learn this. Okay. So yeah. Okay. So now what we're going to do is we will find the sides. Okay. So here, remember that the hypotenuse of a what do you call this one? Hypotenuse here is just what? The radius of a unit circle. Because you see, the radius here, okay, once we rotate the terminal side from here going there, it reaches at this endpoint in which it also, what I call this one, it is also the endpoint of a regular hexagon, which is intersected at this point. You get me? So therefore, your radius would be 1. Hence, your hypotenuse is 1. So if your hypotenuse is 1, that means your base would be h all over 2, which is 1 half. And the height would be h square root of 3 all over 2 or square root of 3 all over 2 because 1 times square root of 3 is square root of 3. So the answer is square root of 3 all over 2. So with that, we can now find our what? Our coordinates here, which is 1 half and square root of 3 all over 2. So we're good to go. Okay? So that's it. That's actually easy. But it gets easier. You know why? Similar to what we discussed on the square, we actually have similar, what do you call this one? Similar right triangles here. Because you see, remember that in a regular hexagon, right? Let me draw it again, right? It could be formed by 6 equilateral triangles, right? So we have 1, 2, and 3, 4, and 5, right? So what I'm trying to imply here is that what would be the angle here, 60 degree? That would be also the angle here, right? 60 degree. Okay. And if you're going to, what I call this one, find the height of the equilateral triangle, just like this one and this one, they would be just the same. Okay. They're just actually the same. Okay. So that means if we're going to find the coordinates here, this one, and this one, is just the same as how we found these coordinates. But just like what we discussed previously, the signs will alter or will differ. So from here going there, we will have exactly 0 degrees. And of course, we have a height here. So we already know that this is 30 degrees. And here, okay, the same thing from here going there, we will also have 60 degree here. And last but not the least, we will also have 60 degree here. Wait, let me draw the leg here. There you go. We will also have 60 degree here. Okay? So that means they are the same. Okay? So if we have one here, we also have one here as well. If we have the base here 1/2, that means we also have the base here as what? Wait, I have no space. We also have the base here as 1/2. The height here as well is square root of 3 all over 2. And the same thing to the other triangles, okay? Remember, this is a right triangle. But what did I tell you? Only the signs will differ. Just like what we discussed before in a square, only the signs will differ, okay? So here, wait. Let me erase the other unnecessary writings here. Okay, there you go. So here we have 1/2 and square root of 3 all over 2, right? So that means in here, we also have 1/2 and square root of 3 all over 2. But again, the signs will differ. So here we will have negative 1/2 and square root of 3 all over 2. Why is it negative 1/2? Because you see, if we're going to get the distance between at this point, like at here, at this point, wait, let me just, right, at this point, right here, but from the origin up to here, the distance is 1/2. But since it goes to the left direction, so this is negative, okay? Or you know what, long story short, if the coordinates are on the first quadrant, both coordinates are positive. If you would go on the second quadrant, which is this way, we have negative and positive. So the negative here is the x coordinates, and the positive here is the y coordinates. Here below, we have two negative coordinates. So x and y coordinates are negative. And lastly, here, we will have only positive coordinates for the x and negative coordinates for the y. You get me? So with that being said, I think you already know what to do. Okay? So here, at this vertex, same value, but the signs will differ. So this is negative 1/2 and negative square root of 3 all over 2. Okay? So if you want me to explain again, well, here, if we're going to get the distance between the origin up to this vertex, horizontally speaking, it would be 1/2 units. But it's since it goes on the left direction, so it would be negative. And vertically speaking, the distance between the origin up to this vertex is square root of 3 all over 2. But since it goes down, so it would be negative, which is why in the third quadrant, we have two negative coordinates. Okay? And lastly here, I think you already know the answer here. This is 1/2 and negative square root of 3. Wait, let me just rewrite it that way. Hold on, let me rewrite it here. So once again, this is 1/2 and negative square root of 3 all over 2. That's it. Okay? So yeah, I think I should have explained this one last in the last recent video that I uploaded. Okay? So with that, okay, let's talk about the angles involved here. Okay? So let me erase these ones. Okay? So here, okay, let me just erase the drawings here. Okay? Because we already found our vertices. I mean, the coordinates of the vertices. Let me just draw the lines here. Okay? So, let's imagine that, let's just say we rotate the angle clockwise. So from here going there, we have a 60-degree angle. Okay? So that means that if your angle is 60 degrees, or let's just say basically other angles that are coterminal angles of 60 degrees, you will have 1/2 and square root of 3 all over 2 coordinates. So 60 degrees and other coterminal angles of it will end up having the coordinates of 1/2 and square root of 3 all over 2. Next, if we exceed further, like we get the angle from here going to this point where it stops until you reach the vertex here, which is this one. Okay, this one, this would be 120 degrees. Okay, so that means if you have an angle of 120 degrees and other coterminal angles of it, you will have negative 1/2 and square root of 3 all over 2 as your coordinates. Okay, so that's it. Next, what if we even exceed further until we reach here? Okay, so that means from start up to here. So here you will end up having I think this is wait. I think this is from 0, then 60, 180. Oh wait, 180, 120. I think this is let me just recall. 240 degrees, okay? This is 240 degrees. So that means if you have an angle of 240 degrees and other coterminal angles of it, you will end up having the coordinates of negative 1/2 and negative square root of 3 all over 2. This is 240 degrees, okay? 240 degrees, okay? 240 degrees, not 210. And last but not the least, here, from start up to here, this is 270, 300 degrees, or this 300 degrees. So here, if you have an angle of 300 degrees or other coterminal angles of it, you will end up having 1/2 and negative square root of 3 all over 2 as your coordinates. So that's it. All right. And we're done. All right. However, I mean, we're done at this part, but there's actually another part. Okay. And this part is, it's still about this one, having an inscribed regular hexagon. But what if we rotate the vertices here in 30 degrees? Okay. Like we have this one. Now, what if we rotate uh, the hexagon itself in 30 degrees? Okay. So this would be the result. Okay. That one. This would be the result. If we rotate the regular hexagon into 30 degrees, like counterclockwise, okay, or rather counterclockwise, we will have this one. So what will be now the coordinates of each of the vertices? Take a break, okay, and see you soon.